All right, so then the second type of special discrete probability distribution is the binomial distribution, okay? So before we give a formal definition for binomial distribution, let's take a look at the following. The binomial distribution is used to model experiment consisting of observations of an identical and independent binary trials, such as yes or no in an election, head or tail in a toss of a coin, dead or alive as a person cancer surgery, male or female in a childbirth, etc. Okay, so yeah, we are not just looking at a single trial, but a finite trial of an experiment having two mutually exclusive outcomes. Okay, so for example, for Bernoulli, we just want to observe yes or no in an election, but for binomial, we want to observe yes or no in, let's say, 10 election or 20 election. Okay, for Bernoulli, we can also observe a head or tail in a single toss of a coin, but for binomial, we want to observe a head or tail in a toss of, let's say, 10 coins or 20 coins, okay? Now, the binomial distributions are generalizations of the Bernoulli trials, okay? So this basically means that the Bernoulli trial is often used as a building block for most random experiments, which include the binomial distribution, okay? Now let's take a look at the definition for binomial distribution. A discrete random variable x has the binomial distribution with parameters n and p if its PMF or probability mass function is given by equation 2. Okay, so in here we have n combination x or n choose x, then we have p of x. All right, this is the probability of the outcome of interest, and this q is the probability of the outcome that is not of interest, while that's the probability of failure, and p is the probability of our success. Okay, where the random variable x runs from 0 to n. Okay, now let's take a look at some conditions regarding the binomial distribution. So one of them states that there should be a fixed number of Bernoulli trials. Okay, so once we have a fixed number of Bernoulli trials, then we have a binomial distribution. The second condition states that each trial of an experiment results in an outcome that may be classified as a success or failure. Okay, I've already explained this in our previous tutorial on Bernoulli distribution. Okay, and also the probability of success P remains constant from trial to trial, and the probability of failure denoted by Q also remains the same. And finally, the random variable X is the number of successes observed in n trials. Okay. All right, so let's take a look at some properties of the binomial distribution. If X has the binomial distribution with parameter or with parameters n and p, then the expectation of the random variable x is going to be np, which is similar to the mean. And also the variance of the random variable x is equal to npq, where q is equal to 1 minus p. And the moment generating function is given in this form, okay? So we can basically testify that the binomial distribution is indeed is a generalization of the Bernoulli distribution, okay? Because if you can recall for Bernoulli distribution, the expectation was P, but for binomial we have NP. And for the variance for Bernoulli we have only PQ, but for binomial we have NPQ. And for the moment generating function for Bernoulli we have this raised to the power 1, but in here we have it for the binomial we have the moment generating function raised to the power n. Okay, so this basically means that the binomial distribution is indeed a generalization of the Bernoulli distribution. All right, so now let's take a look at an example. In a certain hospital, 53% of all recorded births are boys. If 6 babies born in this hospital are selected at random, want to find the probability that 2 of the babies selected are boys, and secondly, more than 4 of the babies selected are boys, okay? So let's take a look at the solution. So let X denote the number of boys out of the 6 babies selected. So X is then the number of successes in 6 Bernoulli trials with probability of success being equal to P. So this P basically means the probability of recording a male birth in the hospital, okay? So thus, X has the binomial distribution with parameters n being equal to 6 and P being equal to 0.53, okay? So we can define the distribution for this random variable in this form, okay? So this 0.53 is the probability of recording male birth in the hospital, and this is the probability of not recording a male birth in the hospital, which is equal to 1 minus this, okay? Then you want to find the probability that two of the babies selected are boys, so this is similar to that, okay? So we have 6 choose 2, raised to the power 2 with the probability of our success, which is raised to the power 2, and there's a probability of failure 1. 6 minus 2 give us 4, okay? So once you compute this, you obtain this, okay? So this basically means that if you are to pick 6 babies, the probability that you are going to have 2 of them being boys is approximately equal to 21%, which is quite low, okay? Let's take a look at the second question. We want to find the probability that more than 4 of the babies selected are boys, and this is also similar to that, okay? So we want to sum from 5 to 6. So this is similar to that. So when x is 5, you have this, and when x is 6, you also have that, okay? So once you use the calculator to compute this, you obtain that, okay? Very quite simple. All right, so let's take a look at another example. The random variable y has the moment generating function defined below. We want to find the distribution of y, and secondly, we want to find the probability that y is greater than or equal to 1, okay? So let's take a look at the first solution. We know that the moment generating function is given in this form, and this can be expressed in this form, which can also be expressed in this form, okay? And we can see that this is similar to the moment generating function of the binomial distribution, okay? So comparing 1 and 2, it follows that y has the binomial distributions. Y has the binomial distribution with parameters n being equal to 6 and p equal to 5 out of 3. So if you are to equate 1 and 2, you can see that n is equal to that. And this is our p, which is equal to 5 out of 3. And this q is equal to 2 out of 5, okay? So then we can define our distribution for y to be in this form, okay? All right, so we want to find probability that y is greater than or equal to 1, which is similar to this, which can also be expressed in this form, okay? So once we input the values, you obtain this, and this is equal to that, okay? This is very quite simple to do. So this is a trial question. I will leave the solution in the description of this video so you can check it out. Please, if you find value in today's tutorial, don't forget to subscribe if you have not. And for your notice, there are no charges anytime you subscribe. It is free of charge, so don't be scared to subscribe to support this channel. Thank you for watching.